So I'm going to talk today about cracking the case of ice shelf fracture, which is to say, I'm going to investigate the ways that glacier crevasses are unique in floating ice shelves. This work has been the product of collaborations with a bunch of wonderful collaborators, and in many cases, they've even led the projects. Many of the students and postdocs have even led these projects I'm going to present. So this list of collaborators includes Seth Olson, Ash Morris, Maureen Denol, Rick Astor, Doug Wiens, numerous folks who put seismometers out on ice shelves, including the Ross Ice Shelf Vibes team, Catherine Walker, Oliver Marsh, Brendan Crowell. This work was carried out at Harvard and the University of Washington, funded by NSF and NASA. And with all of those acknowledgements acknowledged, jump into talking about crevasses. So the most common fracture that one would encounter if you go walk on a glacier is a fracture that usually goes by the name of a crevasse, which is just to say, in this case, a surface crevasse. This painting by Jill Pelto nicely shows what you might encounter. And for the average person who encounters crevasse, they're usually a barrier, they're an obstacle. If you're trying to walk up the glacier, you might have to go around them because they're deep and scary and hard to get around. Fractures on ice shelves are much bigger. They can be enormous. This fracture on the Larsen C ice shelf in 2017 it was over 100 kilometers long, maybe 100 meters wide. And when it breaks off, makes an enormous iceberg. To just be totally clear about some of the language, a crevasse is just a fracture that cuts part of the way through a glacier or an ice shelf. A rift, such as this one in this photo, is a fracture that cuts all the way through an ice shelf. And I use the word crack and fracture interchangeably with crevasses and rifts, both being types of cracks or fractures. Calving then is the mechanical separation of ice from a glacier or ice sheet. In this case, calving resulted in the creation of an iceberg called A68. The letter and number tell where the iceberg is from in Antarctica and its sequential number, respectively. And this is really, an interesting opportunity to study kind of glacier fracture mechanics, and also one of basic importance for understanding how big the ice sheet is, how it loses mass to the ocean. In this huge range of this huge spectrum of different types of glacier crevasses, there's basically been a long history of studying crevassing processes that's basically as old and dates back to really the beginning of modern glaciology as a field in the post-war era. Nye in 1955 proposed a zero stress model where crevasses propagate to the depth where the ice overburden pressure equals the tensile stress. This is actually a diagram from the paper by Weirtman a few years later, because Nye's original paper was like 4 paragraphs long and had no figures. So a different era of publishing. In 1973, Weirtman extended the analysis of Nye, of the zero stress model, to include the effect of water filling in the crevasses, which is to say hydrofractures. Hydrofractures are just water-filled fractures, although usually when people say hydrofracture, they mean that the water plays an important role in the dynamics of the fracture, not just that it is passive bystander, although that's a technical distinction we can get into later. Then in 1976, a really seminal paper that I think is somewhat underappreciated by Smith was the first to use linear elastic fracture mechanics to describe crevasse growth. And to explain why this is important, I'm going to go into a little bit of detail about what fracture mechanics, what some of the basic principles and axioms of fracture mechanics are. So the basic principle of fracture mechanics described by Griffith is that fracture growth converts potential energy into surface energy. So if you think about having a tension sheet of rubber that is stretchy, you put work into, you do work on the object, you stretch it out, and once it's stretched out, it has some potential energy. It has stored elastic strain energy. Then if you take a little knife and you poke a hole in it and it makes a fracture that propagate, that energy is released. It goes somewhere. Where does it go? It goes into creating new surface area. So that surface area has an associated surface energy. And the basic consequence of this sort of energy balance argument is that unstable fracture growth, the kind of fractures that grow suddenly, not the kind that grow incrementally, unstable fracture growth occurs when the rate of potential energy release exceeds the rate of surface energy consumption. So you have this stabilizing process and this destabilizing process. And the basic idea is that energy release rate changes signs. That basically, to make a crack of a small crack, you need to put energy in, but then energy is actually released, and the whole process becomes energetically favorable once the crack reaches a certain length. Said really simply, long cracks are more unstable than short cracks. And I'll just add that if you've made it this far in the talk, you have made it one slide further than my 4-year-old son, who was my practice audience this morning. Linear elastic fracture mechanics, then, is a special type of fracture mechanics. So it's a subset of that more general energy balance. It was first described by Irwin in 1957, who was actually cited by Smith in 1976, the glaciological application of linear elastic fracture mechanics. So if you're a kind of history of science nerd, this kind of thing of, who cited who in papers that are 50 years old is super interesting. Anyways, the idea of linear elastic fracture mechanics is now that unstable fracture growth occurs. It still occurs when the energy release rate changes sign, but now we can relate this to the actual displacements and strains and stresses in an elastic solid, which is a very important case for fractures that grow quickly. And for ice, for example, at short time periods, you can expect that fractures will grow in basically an elastic regime. So now, rather than talking about the general idea of an energy release rate, we can specifically talk about a quantity called the stress intensity factor. The stress intensity factor is a function of the shape of an object, so in this case, the shape of a crevasse in a glacier, the loading exerted on the object, and specifically unstable growth occurs when the stress intensity factor exceeds a critical value called the fracture toughness, which itself is a material property. Spoiler alert, ice has an extremely low fracture toughness. So glass is usually held up as a material with a very low fracture toughness, and ice has a fracture toughness that's approximately 10 times lower than glass. So this gives us our one more step along our timeline. And then the next bit that I'll add is work by Kees van der Veen in 2 papers in 1998, which I think are fair to say are seminal papers in the field. These papers by van der Veen made a number of advances. So previous work had tacitly assumed things like the thickness of a glacier has no impact on the properties of crevasse propagation. Really, the thickness does, so adding more geometrical realism. This was the first study to show that fracture toughness may actually limit propagation. Even though it's low, the stresses that actually drive fracturing glaciers are also very low. So even though ice is very easy to fracture, crevasses don't always propagate all the way through a glacier because they can actually be held up by fracture resistance through the fracture toughness. The van der Veen papers examine the vertical propagation, so they consider how deep a fracture will grow, and rather than just sort of a final state, you can actually consider how it grows through time. They consider both surface and bottom crevasses with and without water, and so this was really a huge advance. And for the most part, the simple models based on the work of van der Veen in 1998 are still used in continental ice sheet models to this day. These models really form a basis for ongoing work. At this point, I'm going to the historical narrative of the development of glaciological fracture mechanics. There's always different ways to tell a story, and there's many different ways to tell a history. This is, obviously one to emphasize and lead into the work that I'm going to present. I would say that since around the time of the collapse of the Larsen B ice shelf, there's just been so much interest in glaciological fracture mechanics that it's just impossible to tell a simple linear historical narrative any longer. And that's really because the collapse of the Larsen B ice shelf was just this galvanizing event for the community that spurred so much interesting research. So for those uninitiated, the Larsen B ice shelf collapsed. Here's a very famous Landsat image from March 7th, 2002, showing this light blue colored material, which is in fact ice that is underneath a thin layer of water, because the entire ice shelf that used to be here has basically fragmented and collapsed into tiny pieces. And now we're just seeing this mixed up mash of water and ice shelf fragments. This event importantly provided unambiguous evidence that ice shelves provide support for grounded ice. On the right, studied by Rod et al. In 2008, very clearly showing that the ice grounded upstream of the former Larsen B ice shelf accelerated upon the collapse of the ice shelf. So this is a way that you can drive accelerated ice mass loss on the grounded part of the ice sheet, and therefore cause accelerated sea level rise. So the summary of this historical context, I would say, is that linear elastic fracture mechanics provides a useful approach to understand glacier fracture propagation. That ice shelf fracture is connected to ice sheet stability, to the broader sense of ice sheet stability, because ice shelves buttress inland ice. This still leaves an open question about how the unique glaciological setting of ice shelves modifies fracture propagation. Remember, the work of van der Veen did not specify anything that was unique to ice shelves. Some of the analysis can carry over, but there's a number of things that are unique about ice shelves. Ice shelves are floating. There are buttressing stresses, which weren't explicitly accounted for in earlier models. There's also flexure. It's hard to flex a grounded glacier because it doesn't have anywhere to go. Ice shelves are floating, so they can have enhanced flexure. There's interaction with the ocean in the form of ocean swell, and ice shelves can also form ice cliffs. So, all of these things are interesting and worthwhile and worth looking into to come up with a more complete picture of fractures in ice shelves. So, based on this kind of line of thinking, we carried out what, to my knowledge, is the first three-dimensional study of ice shelf rifts. The geometry is fully three-dimensional. There's no approximations to the stress tensor beyond the assumption of linearity. Loading is from gravity. The ice fronts have a water pressure load, so a depth-varying water pressure load, and there's a spring boundary condition on the bottom that reflects buoyancy. Deformations are measured relative to a hydrostatically pre-stressed state. And although this is, I think, the first three-dimensional study of ice shelf rifts, it of course builds on numerous previous studies of rift propagation by folks like Eric Leroy, Christina Holb, Anders Leverman, Chris Borstadt, Christine Platt. So really an extension of all of this wonderful work that's been done previously. The basic behavior of the model is that similar to any freely floating ice shelf, there's a net balance of torques along the walls of the fracture, which causes rotation. So for many ice shelf glaciologists, this will be a familiar idea, but to explain in a little bit more detail for the uninitiated, the water pressure and the ice overburden pressure both vary with depth, but since 10% about of the ice shelf sticks above the water line, those two depth varying loads are not equal and opposite at every point in the ice shelf except at the bottom. And for that reason, you get a net torque exerted on the ice front. This is interesting in the context of ice shelf fractures because it means that the top of the rift is actually pressed closed in front of a propagating ice shelf rift tip. The bottom, on the other hand, tends to open first. When we quantify this in terms of stress intensity factors, we indeed see that there is a depth-dependent stress intensity factor with lower stress intensity factors near the top and higher stress intensity factors near the bottom. The main technical conclusion of this modeling work is to develop a parameterization of this flexural boundary layer so that we can capture it in simpler two-dimensional models such as the shallow shelf approximation. And of course, this is, as I mentioned, an idea that will be familiar to many ice shelf glaciologists because, in fact, classic work has shown that there's a net buoyancy torque exerted along the ice front. Now, to get at a sort of more fundamental question about the behavior of marine ice sheets, we can consider how fractures behave in ice shelves without an embayment, ice shelves that stick out into the ocean, such as an ice tongue, versus how ice shelves behave within an embayment, ones that are surrounded by land on three sides. And the important difference between the embayment versus no embayment case, of course, is the existence of buttressing. The idea that there's friction exerted along the sides of the ice shelf. This friction slows down the ice flow, which itself is a buffer against sea level rise, but also affects the state of stress, and therefore we could expect to affect the propagation of fractures. So we do this in our model. We examine a combination of two different parameters, basically the geometry and the boundary conditions. So we consider two geometries and 3 boundary conditions, 6 total models. The boundary conditions that we consider are shown in each row here. So the first boundary condition has basically 0 displacement and then an ice tongue. The second middle row shows a strong margin, which is to say that the friction is so strong with the sidewalls that there's actually 0 displacement of the sidewall ice. And then there is the weak margin case where the friction is so low that there's actually free slip along the sidewalls. And then the 2 columns simply represent margins, rifts that are in the margin of the ice shelf versus rifts that are in the center of the ice shelf. We find that a loss of buttressing can actually cause fracture propagation. This is consistent with an observational correlation between rifting and marginal strength, although it's somewhat backwards than I think some other studies have suggested. Previous work, for example, focused on the loss of buttressing due to calving and the resulting acceleration of ice flow. What we're really arguing here is that a loss of buttressing can also cause calving. So one way to quantify this is by examining the compressive arch, which is basically where you go from a state of uniaxial to a state of biaxial extension, and the corresponding growth of that area of biaxial extension when you lose buttressing. The compressive arch was really sort of described in detail in some earlier work, and we find that it actually provides an okay parameterization of calving behavior, but really the LAFM results have some important differences. At this point, I think it's a natural time to pause and take questions on the first half of the talk. So far, we've basically talked about the history of glacier fracture studies and this 3-dimensional modeling study of ice shelf rift propagation. So I'll pause for 1 minute and sip my coffee. And I guess I don't have the chat window open, but please feel free to speak up because I have to take a minute here to find the chat window.
Thanks, Brad. does anyone have any questions? We don't, I don't see any in the chat.
Sure, I have one.
Yes, please.
Brad. The retrospective on the Larsen B collapse is just a little bit off. The blue color is partly meltwater, but it's also the very narrow calved slabs as the shelf broke up and tipped over. I think Doug McHale's work actually documents the iceberg armada pretty clearly. And that MODIS time series is very powerful for showing how rapidly the shelf collapsed. So while meltwater is certainly a factor and causing the rifts to open up, it is the toppling over in a kind of ice front domino effect that Doug documented. So we do need more observations, surely. The other thing I'd like to mention about A68 and the Larsen C was there's just a hint of the calving of the previous large iceberg from the Larsen C initiated the fracture that eventually became the rift that released A68. Jane Ferrigno and a colleague put out a paper in the late 80s, Antarctic ice front changes that document that previous big berg. The torquing of it probably preconditioned the Larsen C to eventually, many years later, as with the brunt, to accelerate those rifts and eventually release a big berg. So just a complication to the story, if you will. Thanks for listening.
Thank you so much. I'm happy this is being recorded. I have your comments saved now, and I appreciate the additional detail on different aspects of Larsen C and Larsen B. Oh, I see the chat now.
Yes, we have Johnny. I think has a question.
Yeah. Hi, Brad. I just wondered if you could go back to your previous slide and explain the color maps in a little bit more detail, because I think I missed some of the details of the results there.
Yeah, sorry that I went really quickly here. Basically, these are 3 different ice shelves. They're square in map view. So we're looking at we're looking down on an ice shelf. The bottom is the bottom edge is the ice front, and the top edge is the grounding lines, and the vertical edges on the sides are the ice shelf margins. So the ice is flowing from top to bottom, and the color scale is showing the second principal strain. The first principal strain in ice shelves is always positive, and the second principal strain changes sign from positive to negative, or from negative to positive as you approach the ice front. And so this is basically showing whether the ice shelf is sort of extending in one direction only, or whether it's extending in both directions simultaneously. And this has previously been thought, so there's this kind of classic paper by Doak et al. In the late 90s that argued that this is, a good metric for understanding the collapse of ice shelves, and is subsequently, for example, applied to Larsen C. So basically we looked into this, and the yellow dashed lines are showing where our model predicts rift instability, where it predicts rapid rift propagation. And so you can see that it kind of corresponds to the compressive arch, but that the compressive arch probably isn't a great proxy for understanding the stability of rifts. Does that help? I can talk.
Yeah, that's great. Thanks, Brad.
This is covered in the cryosphere paper. So in the discussion section, there's like a few paragraphs specifically about this figure. Oh, this is great. There's a lot of questions in the chat. let's see, who was first? Vivian, do you believe that the breakup of Larsen B will be typical of future ice shelf breakups? Oh, that's a good, predictions are hard, especially about the future. Do I think that the breakup of Larsen B will be typical of future ice shelf breakups?
Well, putting it another way, there was a whole string of ice shelf collapses on the Antarctic Peninsula even prior to Larsen B. So did they follow a similar mechanism? The ice shelf, the melt ponds and the hydrofracturing that broke up Larsen B. Was that characteristic of the other ice shelf collapses?
To my knowledge, yes, although honestly, Chris Schumann is still here and he probably knows the answer to that better than I do. So most of the stuff that, that's my own stuff I can speak in detail about is about the rift propagation so far. To my knowledge, the sort of similar physics is thought to have applied to all of our previous known ice shelf collapses. Whether there's other modes of ice shelf collapse, I don't know. It's difficult to speculate about things that haven't happened yet. It's an interesting question about whether there could be other ways that ice shelves can break up. Like the Thwaites ice shelf is rapidly retreating right now, and I don't think there's much surface melt there. So, maybe that's a case where there's different physics going on during an ice shelf, a rapid ice shelf retreat, disintegration. I don't know if it really counts as a disintegration, what's happening on Thwaites. So I'm not sure. I'm not sure how to answer the question. Let's see. There's okay. Chris is also providing commentary in the chat, so that I think I won't try to summarize that, but I'll just note that it's there. Olga asks, on this slide, loss of buttressing, is ice thickness constant or spatially variable? It's constant, and that's a great point. So all of the modeling stuff that I'm going to present in the talk is with uniform ice thickness, and that's probably a limitation that's worth exploring and lifting. Okay, Chris is providing great references in the chat, so be sure to check those out. All right, we're halfway through the time, so I'd like to continue to go, but this is great. I really enjoyed the interaction. So the next part of the talk is going to dive into more detail about some particular observations. We're going to look at 3 different ice shelves: the Pine Island Glacier ice shelf, the Ross ice shelf, and the Brunt ice shelf. And we're going to specifically focus on a number of different types of observations. So ranging from satellite imagery, heavy emphasis on seismology, on ice seismology, and also using the ISAT-2 laser altimeter. So to start out with the Pine Island Glacier ice shelf, this is work done by Seth Olson, collaborator, and Seth really picked apart these images in quite a lot of really great detail to track exactly the events that led up to the calving of a large tabular iceberg. There's a number of different types of fractures that appear. So at the start, when a seismic network was deployed on the ice shelf, there was already a large rift that had cut almost all the way through the ice shelf, as well as just pervasive cracking throughout the margins of the ice shelf. And then during the time that a seismic network was deployed, a secondary branch of a rift propagated, and we have seismic recordings of that event, and also several wing cracks propagated, as well as the growth of numerous smaller rifts in the margins. You can see here the specific emphasis on the wing cracks and the ultimate calving event, which surprisingly did not have a huge seismic signal, probably because I guess it was counterintuitive to us at first, but it's probably just because it had already broken most of the way through and it actually didn't break that much ice when it finally detached. So the rose diagram on the left is showing the location of ice quakes that Seth cataloged. They come from 3 regions on the ice shelf, which we kind of refer to as the rift tip, which is the orange family, the kind of rift/marginal area in the green family, and the shear margin, the northern shear margin in the purple family. It's notable what's not shown here. So there are basically nearly no events that are detected from the southern shear margin, for example, or from further back in the ice shelf. These families, we can trace their evolution through time and examine the timing with respect to different events in the larger scale ice dynamic and in the ocean. So, for example, we see that the rift tip family was most active leading up to and immediately after calving, and we're fairly confident in the timing because one thing that seismology does is it provides us with very good timing constraints. And so, in a way, these are sort of like aftershocks. After the iceberg, the tabular iceberg broke off, there was this enhanced ice loss from the front that probably took the form of enhanced detachment of blocks and the propagation of smaller crevasses. Meanwhile, the shear margin, the family shown in purple, was basically active at fairly consistent levels throughout the entire time period. You'll notice in the gray boxes in the first row show the noise level. And so some of the seasonal variation that we see is probably just variation in our detection threshold, that we don't see ice quakes that well in sort of the winter because there's lower sea ice, more ocean swell gets through, it actually just makes a noisier environment. So we're actually better at seeing ice quakes in the winter when things are quieter. And finally, the events that happen right along the rift are most active. The green family is most active immediately following the propagation of that secondary branch of the main rift. So again, that was work done by Seth Olson, providing this very detailed chronology of how fractures respond throughout the events leading up to a calving event. For our next tour of observations of ice shelf fracturing, will take us to the Ross ice shelf, and part of a really great collaboration with the Ross ice shelf Vibes team. So this includes Rick Astor, Pierre Bromirsky, and many others. This is a project based out of Scripps and Colorado State University. The Ross ice shelf seismic deployment, which we call Ross ice shelf Vibes, was the biggest in both space and time passive seismic deployment on an ice shelf that's ever been carried out. It was 2 years, and it went along a flow line and a cross stream line along the Ross ice shelf with elevated station density near a large rift. So you see that plan view description there on the top, and inset map reminding us where the Ross ice shelf is, and on the bottom a profile giving some context for the sort of geometry of the ice shelf. Of course, great vertical exaggeration. And this seismic network recorded many things, and there's been, I think, 3 or 4 papers published so far about the observations. One that is particularly interesting and to my knowledge unprecedented are these families of repeating ice quakes that happen during periods of strong ocean swell that recur so regularly in time that they form spectral peaks. This is basically a consequence of the Dirac-Combe theorem. And the idea is basically if you have events that are spaced apart in time by some amount of time t, that if they're perfectly regular over a sufficiently long window, you form spectral peaks with a fundamental mode at 1/t. And so, by example, if you think about a piano with, A below middle C being at 440 hertz, that 440 hertz corresponds to actually 440 oscillations per second. And what we're seeing here at a fundamental period of about 0.1 hertz is an oscillation, a repeating event, which is an ice quake, which is happening essentially at once every 10 seconds. So once every swell, every ocean wave that arrives causes one tiny little ice quake to pop off. So you can see that in the bottom figure here, where we measure the ocean swell by filtering the seismic data to what we call the swell band, 0.03 to 0.12 hertz. And then the blue trace shows what we call the ice quake band, which is a higher frequency band showing the impulsive seismic wave arrivals. And you see that they occur approximately phase locked, but there's a little bit of variation, which we explain with a fracture model that I'll show you in a second. Two interesting observations is that the ice quakes show thresholding and hysteresis. That is to say, the ice quakes only occur beyond about 1 meter of swell amplitude. So they only turn on once the swell reaches a certain critical amplitude. And then once they turn on, they persist even after the swell goes to lower amplitude. For this reason, we do not think that these ice quakes correspond, for example, to the direct impact of ocean swell on the ice front. There's a few reasons that we think that, but I think the main reason is that it's difficult to explain a threshold or a hysteresis behavior in terms of a direct wave impact where we would expect sort of a simpler system. So for that reason, we modeled the effects of swell and flexure. And this is a linear elastic fracture mechanics model. It's very much in the spirit of Van der Veen 1998. And to that model of Van der Veen 1998, we add two effects, or specifically, we look at two effects. The modeling is done very differently, so we use a finite element approach, whereas Van der Veen used sort of simple models that were solvable analytically. So the two effects we look at, ocean swell and flexure. The effect of ocean swell is actually interesting and somewhat complicated. Ocean swell both changes the stress balance at the ice front, and it also propagates into the ice shelf and causes a local effect on crevasses. And both of these actually affect stress intensity factors. Ice front flexure causes tension and a compression, a relative tension and relative compression of the ice front. The elevated tension favors crevasse growth. The relative compression inhibits crevasse growth. Oh, and one more thing to say is that away from the front, we recover the limit of Van der Veen 1998. In more detail, so this slide gets somewhat technical. Feel free to just think about the cartoons in the last slide if you like. This is showing that there's actually several boundary layers as one approaches the ice front. So this is a wonderful mechanics problem. There's really beautiful layering of these different regions. So far away from the ice front is the right-hand side of these two plots. The left plot is showing surface crevasses, the bottom right. The right plot is showing bottom crevasses. And we'll just focus on the heavy blue line for now. The heavy blue line is the finite element simulation. So all the way to the right, at distances greater than sort of tens of kilometers, we recover the Van der Veen solution for both surface and bottom crevasses. The blue lines are showing the opening mode, and the orange-yellow lines are showing the shearing mode of fracture. Now, as one approaches the ice front, the first thing that happens is you enter the zone of flexure. So when you get to within one flexural gravity wavelength of the ice front, you start to feel the effects of flexure. And the way that you experience flexure depends on exactly how you treat the ice front. So we've done two different things here. I've looked at a case of just a traditional bending moment following kind of re 1968. And we've also looked at the case where there's a buoyant foot attached to the ice front, which is similar to Till Wagner's model from 2014 that was also explored by other folks in the Scripps group. In any case, as you become even more closer, as you get to sort of within tens of meters of the ice front, you actually start to notice the existence of the freeboard. You start to realize that the state of stress is affected by the part of the ice shelf front that's above the water line. And that further modifies the behavior of fractures. It actually, the fact that there's a free surface, a vertical free surface that sticks out above the water actually reduces the opening mode fracture because there's lower tension in that region. So all that's to say there's kind of wonderful richness of fracture behavior in a relatively simple system. Just this is a uniform thickness ice shelf that's freely floating. We can also examine the effect of
Bradley, do you
swell.
mind if I interrupt you 1 second?
Please do.
So, yeah, sorry. There's a bit of a chatter going on in the chat. In particular, there's a question from Vivian. I was just wondering, Vivian, if you'd like to unmute and perhaps ask your question.
I was just wondering, would this discussion also, a similar discussion, apply to the effects of tides or storm waves?
Yeah, and so here, let me just do this. Seth Olson wrote a great paper about the effects of weather and tides. Where did my Zoom controls go? This is what happens when you use too many screens. I lost my share button, which I'm going to have to find. Oh, there it is. This one. So in this paper, Seth Olson looked at the effects of ocean tides and thermal stresses, which are mostly affected in this data set by synoptic weather patterns. And so this is looking at seismicity along a rift in the Ross ice shelf. And there's a very clear correlation with the tides, which is interesting. And what we think is happening here is that as the tide goes down at the ice front and it causes the entire ice shelf to tilt and to stretch out. And as the ice front goes up and the ice shelf tilts the other way, it causes the fractures to compress. And it turns out that the ice quakes mostly happen when the ice shelf is extending and being pulled open. The ice quakes that Seth observed are also strongly correlated with temperature, with virtually zero lag time. So we were trying to measure what the lag time was, and again, seismology provides great timing, but the ice quakes basically happen within the resolution of the temperature data. So I think there were 15 or 30-minute weather data. I don't actually remember, but so that basically suggests that these are happening, in very shallow ice layers. So these are along a rift. So we think they're happening basically in the melange and along the walls, the ice cliffs. That these features have elevated fracture due to temperature patterns and also due to the tides. So
thanks, guys. Perhaps I should also say there's lots of great material from Chris Schumann in the chat. Just recommend people check that out.
Yeah, I am gonna make sure to copy all that because I know it doesn't get saved with the recording. So that was to speak to the sort of temperature and tides. We have this other piece, which is the swell, and we incorporate this into our model. So these 4 panels are showing opening mode K1, shearing mode K2 in the left and right columns respectively, and surface and bottom crevasses at the top and bottom columns, or top and bottom rows. And basically the way that I'll summarize this is by saying that we've developed a parameterization which is suitable for large scale models that incorporates the effects of ice front flexure and ocean swell into the widely used Nye-Weirtman model. So a relatively simple way to couple the elevated stresses due to ocean swell and to relate those to ice shelf fracture growth. The last project that I'll highlight is a measurement of fracture topography using IceSat2, which of course is building on a sort of lot of work previously done looking at ice shelf topography using altimetry, including work with done by Helen Fricker, Catherine Walker, Alex Gardner, Suji Wang, and others. The Rift case study on the Halloween crack is a particularly interesting opportunity to pursue because we have a long history of work on the Brunt ice shelf carried out by the British Antarctic Survey. So this is a very well understood environment, even though the Brunt ice shelf is in many ways a weird pathological ice shelf. It's got great data, including active field campaigns with GPS instruments, which is what's shown on the right there. And on the left, I'm just showing some nearly unprocessed altimetry data, which is highlighting the fracture that you can see on the right. Those are the same place. We have developed, really, Ash Morris, who's leading this project. He's a postdoc at UW, has developed a rift detector. And you can see on the right that comparisons with optical imagery are favorable and show that, they basically provide a validation of our rift detector. So when we look at the Halloween crack, it's actually really useful to have the field-based imagery because we see things like this, these detached blocks that are floating in the middle of the rift. At first, we thought these were actually parallel fractures because they show up in the altimetry data as being two parallel depressions. But it turns out what we're actually seeing is just the rift filling blanche on both sides of the big blocks. And again, what's great about the Halloween crack is that we actually have ground-based geophysics. We have GPS measurements. So looking at the two stations on the different sides of the rift, we can resolve the relative motion into shearing and opening components and measure the total opening along the fracture. And what we observed is not exactly what we expected. So it turns out that the rift walls are moving apart faster than the GPS stations on both sides of the rift. So I'll say that again. The two GPS stations are moving apart at some rate. The rift walls appear from the altimetry measurements to be moving apart more quickly than that, which we think means that there's erosion going on along the walls, that there's blocks that are breaking off and falling in and forming the melange. Now, this is maybe a process down to the scale of like 10 or 20% of the total opening, but it's worth understanding because it relates to this idea of cliff instability. Now, this isn't exactly the ice cliff instability, for example, of Bassis and Walker 2012, because their model is really only applicable for taller cliffs. Here, we see that rift wall erosion actually occurs at a much lower threshold than predicted by Bassis and Walker. And we haven't done the fine scale modeling of this yet, but the model that we developed based on the Flexure and Swell on the Ross ice shelf could be applied here to examine the shearing mode detachment of blocks along the rift wall. And the evidence that this isn't crazy actually comes from this, this airborne photo, features that we really can't see that well except in the highest resolution satellite imagery. And even then we don't really see this fine a scale. We see detaching blocks. And so it's, based on photos like this, we think it's not crazy to think that there is actually mechanical erosion of the rift walls that's taking place. So with this, I'll spend a minute to summarize before taking more questions. So we pose the question, how does the unique glaciological setting of ice shelves modify fracture propagation? And we basically looked at 4 facets of this question with the statements that ice shelf rift propagation is stabilized when strong buttressing is present. Ocean, swell, and flexure both can enhance crevasse growth. That ice quakes track ice shelf fracture on the Pine Island Glacier ice shelf. and that ice cliff fracture occurs along rift walls, perhaps at lower thresholds than previously thought. And the message that I'd like to leave you with is that the results presented here highlight the use, but also the limitations of simplified fracture models. I think we put a lot of trust as a community into elegant, sort of applied math flavored models, which I love. My training is kind of in classical mechanics, classical continuum mechanics. So I'm the biggest fanboy of this kind of modeling, out there. However, I think that when you sort of look into the observations, you also realize the limitations of this approach. And I think the observations really highlight that a more detailed observational appreciation of fracture is really going to drive further progress in the study of ice shelf fracturing. So I'll say thank you for your time, and note that all the code presented here are available on the author's GitHub accounts. So thank you very much, and I'll love to keep the discussion going.
Thanks very much, Bradley. That was a fascinating talk. Do we have any questions from the group? I see Seth is clapping. Perhaps I should get some canned applause to play at the end of these. Johnny is also clapping now.
You can do like canned applause, or maybe canned laughter as appropriate. Yep, we are still, that's right, still waiting on Chasm 1. It made us think it was going to break, but then didn't. Yeah, Chris?
Yeah, the Brunt is just a terrifically fascinating place, and not just because Haley Station is there and they have such a long experience working around the McDonald ice rumples, where the Halloween crack radiated from rapidly, as did eventually, you call it the North Rift, we just refer to it as the Fast Rift because it formed so quickly. But Chasm 1 and Chasm 2 are many decades old, and the influence of the melange is the thing that just mystifies me in some of these really big features. Even the rift that formed A68, I mean, it was there for many years before it finally started to cut through suture zones and move north, and so there is some mystery to the triggers on, when these things finally decide, yep, now's the time. And even then, there may be holdups and misdirections, as we saw at the north end of the Larsen C rift, where it got farther north and then turned around and cut sideways along a suture zone before it finally broke free. I mean, these are very complicated mechanical substances that must be a real headache to model. I guess that's where I'll close with that thought.
Yeah, but I think your comment and really highlights, I think a way forward in the modeling, which is, in a way, the LAFM problem is kind of it's kind of easy. Like once you set up the LAFM part, you can then go to the observations and say, like, what about melange? Like, I don't think there's been enough LAFM work with melange. Just blanket statement. I don't think there's any study looking at LAFM with melange. That's a off the cuff comment, so I hope I'm not offending anybody there, but I'm pretty sure it's true. So like we could incorporate the effects of melange in our model, or if somebody else wants to do that, there is a crevasse code. I didn't put the name. If you go to that GitHub link at the bottom, it's called the crevasserator, and so you can download the crevasserator and put melange in it. It's fairly easy to work with. And similarly, the observation of fast versus slow rift growth, I think is totally worth understanding. Olga?
Nice talk, Brad. Yeah, another nice variation of the same talk. I have a question of rather confusion about the last part, ice cliff. My impression was that Jeremy and Catherine developed the ice cliff. It's not instability, but anyhow, for the grounded ice, meaning the cliff, the ice is not floating. Is it correct, or it's just my misunderstanding, misremembering?
I can't. I don't know per se about their motivation. There are parts of the paper that discuss stuff relevant to ice shelves.
Because the reason I'm kind of asking is that you are looking at the floating part. So as you know, the stress regime is fundamentally different when you have the ice which is grounded and it is a vertical cliff compared to what the kind of opening rift, what you're looking over here.
Yeah, agreed. The yeah, I have a lot of thoughts going through my mind at once. I'll try to organize them. Near the boundary layer of the ice draft, it may not matter as much. I'd have to think about it more. But you still have some far field tension that enters the problem, which would be different for grounded and floating ice. But I think that some
and locally, because
here
you're floating. So I appreciate that, yeah, there is a boundary layer and everything, but when the ice is grounded and truly grounded, you have the basal shear, which is pretty much everywhere. And that, my understanding, was a part of the consideration. Again, I may be wrong, so I guess, yeah, it is a question about like how you treat your quote unquote ice cliff.
Yeah, again, you know, I guess one thing to highlight, this is something you could do in like 5 minutes with the crevasserator code. So it's something that's readily testable. My guess is that the main thing is the flexure zone change, because right, grounded ice can't flex because it doesn't have anywhere to go. It can't flex downwards into the earth because it's supported. And then the thing I'm trying to think through in real time is how that interacts with the with that sort of boundary layer near the ice draft, because that's you know the small scale feature, but it's matched asymptotically to the flexure zone, and so I'm not sure how that. That it's totally good point. It's worth looking into.
Okay, thanks.
Many thanks, Olga. I see that Chris has his hand up. I'm not sure if Christopher wanted to ask another question.
Sorry, that's Relic.
I like your comment about the T-shirt idea. Yeah, it would be great to get some merch for a model. That would be wonderful. Do we? Pardon, sorry.
I was going to ask what do we want to name the T-shirt? Fast Rift or North Rift or both?
Crevasserator.
Oh, the Crevasserator, yeah. We're having a logo design contest within the group. Awesome. Well,
do we have any final questions from anyone? I'm a bit conscious of the time.
I guess the one thing I would mention is the Ferrigno and Gould paper is based on data that has now been lost. And for those of us that know these things, can evolve over many decades. It's sad to think that some of the data that has been published on is no longer available. And it's just a lesson for us as a community going forward to try to prevent that from happening. So these GitHub repositories and things like that, even NSIDC itself, are resources we're going to have to defend and support in the years ahead. So just stop there.
Thanks, Chris.
I'm looking through that paper right now. Thank you for sending that.
Thank you ever so much, Bradley, again for speaking today. I very much look forward to uploading this talk and adding it to the online collection. Hopefully, we'll get you back in 6 months or a year, however soon we can try. I hope everyone has a wonderful rest of the day. Thank you for joining us, and we'll see you all next week.
Great. Have a good day, everybody.